minimum thickness of a gas or vapor layer beneath an impacting drop onto a solid substrate.
Yes.
Over to you.
I'm Guillaume Riboux. This work was carried out at the University of Sevilla with José Manuel, and some part of this results with Paola Garcia Reiro. So this is the outline of this presentation. I will introduce the problem. I will talk about the isothermal case, and after the dynamic Leidenfrost case, and after I will conclude. So it's important to note before to start that we have, if we fix the velocity of the drop and the radius of the drop, as well as the property of the drop, we want to obtain a model to have the minimum thickness of this vapor or gas layer beneath this drop, and you need a model which will work in the two cases, so in the Leidenfrost case and in the isothermal case. So if we heat the substrate, and after we cooling this substrate a little bit to reach the temperature, the ambient temperature, the model which is will be the same in the two cases. You cannot have a minimum thickness with a certain scaling in the isothermal case and other scaling in the dynamic Leidenfrost case. So I record the expression the expression obtained for Mond and Brenner and the group of 20, for which they are able to determine, or they obtain the scaling of the dimple, the height, the thickness of this dimple, of the air layer beneath this drop, and this scaling. It's a power law of the Stokes number. The Stokes number is like a Reynolds number based on the viscosity of the air. So it's a Reynolds number multiplied by the ratio of the viscosity between the liquid and the air. So with this scaling, exposed also by Devaraj yesterday, we can determine which is a time scale for which we have the formation of this dimple. And if we do this calculus, we have this Stokes, the evolution of this scaling, this time scaling as a function of the Stokes number in the power law minus 2/3. So all the results that I will present today, we need to rescale the time with this Stokes number power law. After that, Kolinsky performed experiments and shows that this minimum thickness evolves in time. You have the interface, and below this interface you have the air, and this interface is evolving in time. And observe the lift-off effects at the minimum thickness increase in time. So the air layer perform a lift-off of the impacting drop. After that, we have the results of Shirota, the group of 20. They perform also experiments and observe different regime beneath this drop. So you have a different regime depending on the temperature. The last results were at ambient temperature, and now we have heated substrate. So for different temperature of the solid, you have different regime, and they observe that the minimum thickness in this vapor layer beneath this drop evolves at the square root of the 3 times the dimensionless time result from the Wagner theory. They also observed the diagram, so they plot the diagram, the substrate temperature as a function of the impact velocity, and they observe the different regime, and they are able to determine which is the boundary for which we observe the dynamic Leidenfrost regime. So there is no contact between the drop and the solid substrate. So if we want to determine this boundary, for which we haven't contact, which is important in application, because if we haven't contact, the air act as an insulator, and so you cannot transfer heat from the solid to the liquid. So to predict this transition or this temperature called Leidenfrost temperature, we need the minimum thickness of this vapor layer. The excellent work of Ciantello and Losé, they perform experiments like the Shirota experiments, and they obtain the same evolution for the position, Rn is the position of this minimum thickness, the radial position of this minimum thickness, and observe the same results, which is the square root of 3 times the dimensionless time. They obtain also in the 80 substrate this scaling of the dimple height, which was observed by the same group, 20 group for the isothermal case. And they are able to determine the minimum thickness with these techniques, laser techniques, using the sapphire, solid sapphire to have a view, and they are able to determine this minimum thickness as a function of the velocity. They plot this diagram, Leidenfrost, solid temperature as a function of the velocity, and we see the transition here with a red line, this transition for which we have a short contact and we have contact. We have no contact, sorry. They publish also in this paper results because they are able to determine when the hole is appearing in these images. So when you have this hole, the black dot here, you have contact. Because the gray scale here is related to a thickness of the vapor layer, they are able to determine which thickness the hole is, you have the contact. They do this experiment 20 times, and observe that the height of this thickness for which we have contact, it's between 250 nanometers and 400 nanometers. So this is why we are not able, it's impossible to determine minimum thickness below this range. Why? Because this is the site of asperity or impurity in the air or in the solid substrate. After that, I expose just rapidly this results from Kim. So he used a sphere, heated sphere at 1000 degrees, put it in the liquid, and measure the evolution of the temperature in the sphere as a function of the time, and observe this cooling phenomenon as a function of the time. He adds to the fluid nanoparticle and observe a different behavior of this cooling. So this result explains that the presence of particle or impurity destabilizes the vapor layer around the sphere and produce the contact with liquid. Finally, I will use extensively the results that we have published with José Manuel in the GFM in 2022, for which we are able to determine this minimum thickness using the results, using the experimental results by Ciantello and Losé. And we perform, because we know the radial position of this minimum, which is a square root of 3 times the dimensionless time, we are able to determine the velocity of this point, which is called Vm here in this presentation. We have the length of this region, which is called Hm, and in this region we have an overpressure, which is called delta Pm. So we use this result and Now we would like to determine the minimum thickness in the isothermal case. For do that, we perform numerical simulation using basilisk. So the temperature is ambient temperature for the solid. I introduce the Stokes number, the Weber number. We varied in the large range these two dimensionless number. We fix the ratio between the density of air and liquid to the true density ratio, also for the viscosity, and we obtain the evolution, this evolution of this air layer beneath these drops. As exposed before, we introduced this scaling to scale the time. So we define general dimensionless time with the impact velocity and the radius of the drop, and we define tau, rescaling by this Stokes number as I have presented before. So beneath this drop, we have flow rate conservation, and we have two flow rate per unit length. One is a Poiseuille flow rate, the other one is quite flow rate, because we are moving in the frame of reference with this radial position, which is the radial position where we have the minimum thickness, and we have the expression of Vm, Hm, and delta Pm. So we are able to determine the pressure gradient, which is in this conservation flow rate equation, and we have two cases. So one case is that this region can be the capillary length of this inertial length Hm. So in one case, if we have this capillary length, we have this expression for the minimum thickness, and note that this expression was obtained before by Duchemin et Josserand. If we use the other length, we have this expression. Both expression depends on the dimensionalized time, Weber and Stokes. The second one don't depend on the Weber, but we have an expression function of the time, of the function of the dimensionless time. So now we would like to compare with experiment. We compare with the experiment with Chantello and Lossé, the Ritter. So we have the minimum thickness as a function of the velocity. And to do so, first we need to know at which time we have the minimum thickness, because this minimum thickness evolves in time. So we can see here with this numerical result that this time is close to 12. So the minimum in time of the minimum thickness at 12, tau equal to 12. So if we put tau equal to 12 here, taking into account an idea proposed by James Brittles. So James Brittles say this vapor layer is very thin, is too thin, so you need to take into account gas kinetic effect. How do you do that? You used effective viscosity of the gas, which is, in our case, we have taken this expression from Zhang to take into account this effect of the thinning vapor layer. So in this expression, you can see that you have the Nussen number. The Nussen number is the mean free path over the scale, which is the scale. This is the mean thickness. And we take into account for the mean free path the overpressure at this region, which is delta Pm. So we do that and obtain this curve, the theoretical curve, and a good agreement with two sets of experiments. We look at the dynamic latent frost regime. So this case is a simpler case. Now it's more complicated because we are heated the solid substrate. So the same, we used the experimental result obtained by Chantello LOC, heating the substrate, measuring the minimum thickness, and we have this different curve. Each color corresponds to different temperature of the solid. So now we have we are heating the substrate, so we are evaporating the liquid. In this case, the liquid was ethanol drop impacted into the solid substrate. So we have a evaporating flow rate. This evaporating flow rate can be determined by the heat power per unit area, taking into account the conductivity of the vapor. So we have the ethanol vapor beneath this drop, and we put this in our mass flow rate conservation equation. So this flow rate conservation equation can be described with this variable. So we have y, where this variable beta star, which depends on the property of the liquid and the vapor layer, the different temperature between the solid and the boiling temperature of the ethanol, which is ethanol here. And this is a quadratic equation. So quadratic equation, we have the solution. We can calculate beta star. With beta star and the different viscosity of the air and the vapor layer, we can determine y. And with y, with this expression, we are able to determine HEM. HEM, note that Vm is known. L is the scale of this region, which is the capillary length or the inertial length, which is HM. And we have Y and the Stokes number. So we are able to determine the minimum thickness, taking into account the heated of the solid substrate with these two lengths, HM and L, the capillary length. The expressions are the same, but Y is not constant. This is the same expression that in the isothermal case, but Y is not constant. If you have air instead of vapor, I don't put it here. Y it's 6. No, I don't put it here. So Y is 6, is constant. So the same expression. The procedure to calculate this. Because I put the procedure, because you need to take into account the temperature. So it's not easy. You have U and R. We have fixed the Weber number. So we have the Weber number. Now you need to take into account the temperature. Which is the temperature? We have take the average temperature between the solid and the boiling temperature of the liquid, which is in this case, in the table, it's 778 for ethanol. So with this temperature, we calculate the viscosity of the vapor of ethanol and the viscosity of the air at the temperature. We calculate the density of the vapor, taking into account the effect of the temperature and also the overpressure at this region, where you have the minimum thickness. We calculate the B star, which depends on all the variables that I have calculated before, and taking also into account in the capacity of the vapor at constant pressure, the evolution with the temperature. We calculate Y, which depends on all these variables, and finally HEM. But if we finish now, we haven't taken into account the gas kinetic effect. So we need to take into account the gas kinetic effect. We calculate the mean free path taking into account this average temperature and the Nusselt number. So lambda particle over HM. We calculate the viscosity And we take into account the conductivity and the effect of the gas, the gas kinetic effect into the conductivity of the vapor of ethanol. Sorry. And now we calculate another term B star, another term HEM, and we did a loop to converge to the correct value of HM. So in this procedure, we have taken into account the real propriety of the vapor and air at the average temperature, and we have taken into account the gas kinetic effect in the model. So you have a Python script published in the supplementary material of this publication for which this procedure is described. In capillary regime, we have this expression, the same expression that in the isothermal case. We compare to the results obtained by Chantello and Lossé, and we have a correct agreement with experimental result in the case of the inertial regime. And we observe some discrepancy between the model and the experimental measurement at largest temperature. Why we have this? First, we can see that if we increase the constant in this expression, okay, so the constant was 1.25 here and 1.7 here, we have a correct comparison between the model and the largest temperature obtained by Chantello and Lossé. And we think that the agreement is not so good, because if we plot the minimum thickness compared to the inertial scale, which is the case of this line, we observe that they are close to 1. So the slender, use the slender theory to this case is not so good, because it's not slender, this region, in this case. So I finish with Leydig frost temperature. We have the expression for the minimum thickness, so we are able to determine the Leydig frost temperature for which we haven't contact between the drop and the heated solid substrate. So this is an experimental measurement of Chantello and Lossé that I show you at the beginning of this presentation, and 2 points from the Lee and co-author in soft matter. So, as I explained at the beginning, we think that we have contact if HEM has a thickness equal to the size of the impurity on your solid in the air. So, if we fix the HEM equal to the size of impurity, we can calculate Y. And if we can calculate Y, we can determine the different temperature between the solid and the boiling temperature of the ethanol. We do that for 3 sizes, which are 250 nanometers to 360 nanometers, and we observe a good agreement with the experimental measurement. Okay? Now, if we believe that we are right, we go in this diagram and we take, for example, 1.5. We take 1.5 and we need a temperature larger than 500 degrees to observe no contacts, to observe the Leydig frost regime. For all below, you have contact. And now, if we look at the Chirota observation, the liquid is the same. So this is ethanol. And you have the Leydig frost temperature. So for temperature larger than this one, you have no contact. Below, you have contact. And you have this experimental point. But if you look at 1.5, you have not 500 degrees. So what happens? we think that in this case you have contact, but you have a bubble, a vapor bubble attrapped beneath this drop, which is a relevant process for application. You don't need to know if you have a small contact with a solid. You need to know if you have this bubble or not this bubble. So, because we have this bubble, which evolves with this contact point, and this contact point evolves in the square root of 3 times the dimensionless time. So you have also the velocity, which is Vm of this point. So you can calculate the volume growth rate of the vapor bubble in this in this region. Also the mass flow rate of the vapor produced in this dipole, and equaling the both, taking into account also the density of the vapor. You are able to determine the temperature in this case. So we have contact, but you have the vapor, this bubble, evolving in time beneath the drop. And we compare with this model, and so it's great, it's correct. Only for this point, this is the greater impact velocity. And we think that in this case, the frame rate is not sufficient to observe the transition for which we have no contact and contact, because this transition for this velocity is the contact is done just 30 seconds is done at a radial position close to the center. So it's difficult to have this measurement. So this model takes into account the real property of all the property, vapor, air, as a function of the temperature. We have taken into account the Knudsen number, the effect of gas kinetic effect, and we are able to determine the minimum thickness as a function of the dimensionless time, not so only on the Stokes and the Weber number. We have proposed this model, and we see that our model is able. I think it's able to determine the minimum thickness in isothermal case and practically all the dynamic Leidenfrost case. And with this minimum thickness, we have shown that it's possible to determine the Leidenfrost temperature. So thank you very much for your attention.
Thank you, Guillaume. Thank you.
Perfect in time.
Perfect in time. Quick question or two.
Thank you for a very interesting talk. My recollection of James Brittle's experiments with the kinetic effect is that to reproduce the data from Kalinsky, he also needed to include disjoining pressures.
Sí.
I don't think you mentioned disjoining pressures, but do you have a feeling on what they might do to this kind of setup?
I didn't know.
Okay.
I didn't know. Really, I didn't know. We haven't taken into account this pressure.
Previous question. I want to ask you whether you think that the Leidenfrost effect is like a metaptosis for the original balance between the external overpressure and the lubrication pressure, to another case where this overpressure is balanced by perhaps the disjoining pressure, like Van der Waals or some other type of forces. Well, this is another way of expressing the Leidenfrost effect.
Okay. Okay. I don't know. I think this model works. This model works, but perhaps taking into account this Van der Waals effect, or perhaps It will be better, or I don't know, but for me, it works.
But it will help you define the minimum thickness of the finish, right? It will be there in that balance.
So can I say something? So the thing is that the disjoining pressure, so you need distances of 10 nanometers, 20 nanometers, and here what you have is 200 nanometers, so disjoining pressure, the effect is 0. So forget about disjoining pressure in the Leidenfrost, please. So, no. 20 no. It plays no role.
For the dynamic. But actually you have a lot of parameters or a lot of physical effects. Did you try to identify which ones is dominant to others, or whether some of the terms that you have implemented are maybe not relevant and so on?
We try. We start taking into account, for example, the viscosity of the vapor, taking into account the temperature, and we see that is not. So we take into account the density, the evolution of the density, etc., etc. And you need all.
Because for me, the main effect is that you have vaporization that increase the radiation pressure. That's why.
Yeah. But,
Okay, perhaps we should end it there. Thank you. Yeah.
What?
Thank you again.
Yes.